Hello, and welcome to a lecture on radiation from electric current in free space. My name is Steve Ellingson. The objective of this lecture is to explain how to compute the electric and magnetic fields resulting from a current distribution, which we'll give the name J, in free space. So this current distribution creates a wave which travels away from it. And what we're going to compute here is the electric and magnetic field intensities in response to that current distribution. So here's the organization of this talk. First, just a brief reminder of the starting point, Maxwell's equations. An introduction to the magnetic vector potential, which is really the tool that we use to solve this problem. The vector Helmholtz equation, which is simply a differential equation for the magnetic vector potential in terms of the sources, the current distribution. Along the way, we'll end up talking about wave number, and then the solution of the vector Helmholtz equation. And then the bottom line is this, starting with currents, having units of amps per meter squared, we come up with the magnetic vector potential, A. From that, we can get the magnetic field intensity, which has units of amps per meter. So the bottom line is the last slide, and everything else leading up to that is how we know that that final answer is in fact the answer. Okay, first, Maxwell's equations. I'm going to give them to you in differential point form and in the frequency domain. So here's the Maxwell-Faraday equation that relates the magnetic flux density to the spatial changes in the electric field intensity. Here's Ampere's law, which relates the electric field to changes in space of the magnetic field intensity. And here is the current of interest. So that's the source that's going to generate the fields. Here's Gauss's law. And then Gauss's law for magnetostatics. The divergence of the magnetic flux density is 0. Now this is not exactly the most useful form for solving this particular problem, so we're going to make a few modifications here. First, we're going to take the Maxwell-Faraday equation, and we're going to convert B to H. So the way we do that is simply to replace B with mu H. Then we'll take take Ampere's law and convert the electric flux density into electric field intensity. That's simply replacing D with epsilon E. This way now we have coupled equations for E and H, and also in terms of the source J. We're going to assume there's no free charge, so we don't really need to account for Gauss's law for electric fields, but we will retain and exploit Gauss's law for magnetostatics. Okay, now the magnetic vector potential. Here's a starting point. Any function, and this is a mathematical argument, any function whose divergence is 0 is equal to the curl of some other function. So just based on that much, we can be sure that there is some quantity A, and we haven't really said what it is yet, that satisfies the relationship that the curl of that function A gives us the magnetic flux density. So this is just a mathematical idea. Also see that this satisfies Gauss's law for magnetostatics. Gauss's law for magnetostatics says the divergence of the magnetic flux density is 0. We can substitute this relationship in for B. We get this expression, and we know from vector identity, from a vector identity, that this is equal to 0. So everything works here. This principle is consistent with Maxwell's equations. It's useful to know that the units of the magnetic vector potential can be written as Teslas times meters, or as Webers per meter. So some people think of this as being a magnetic moment or magnetic torque, or you can think of it as magnetic flux per unit length. for our purposes, magnetic vector potential is simply a mathematical device, tool, that allows us to solve Maxwell's equations. Okay, so let me say specifically why this is helpful. So here's, again, the Maxwell-Faraday equation. I'm going to now substitute H with the defining relationship for the magnetic vector potential, and now I must, of course, divide by the permeability, because the magnetic vector potential is defined in terms of the flux density, not the field intensity. Then multiply through, and I get this revised form of Maxwell-Faraday equation. I'll gather up everything on the left-hand side, and I find that the curl of the electric field intensity plus j omega times the magnetic vector potential is equal to 0. What we do is we define this quantity in the parentheses to be equal to some quantity, and we'll say that that quantity is equal to minus the gradient of capital phi. Now, the reason we do that doesn't become apparent, or might not be apparent right away, but it'll become apparent in a moment. If we make that substitution, we can now write the electric field intensity as minus j omega a minus this quantity, the divergence of, the gradient of phi. And as before, from the defining relationship, we can write H as 1 over mu times the curl of A. Now, what we've accomplished by doing this is we have mathematically decoupled the electric and magnetic fields. In other words, now we have a relationship between E and H and an independent quantity, A. So the idea is now if we can find what A is, it becomes straightforward to get E and H. Whereas before, we had coupled simultaneous equations. Okay, so now what the heck is this quantity capital phi? Well, again, here's how we defined it. I'll point out that phi can be any function, so in some sense it doesn't really matter what it is. And the reason is because the curl of the gradient of any function is equal to 0, and that's by a vector identity. So no matter what we choose for phi here, we're good to go. There is a preferred choice, though, and to see what it is, we have to go a little bit further down the road, having made these decisions that we've already pointed out so far. Okay, so here we go. Here's Ampere's law. We'll make the substitution H. We'll substitute with the defining expression for A. E we'll replace with this expression that we just derived for E in terms of the magnetic vector potential. On the left, we have the curl of a vector, and that's a well-known vector identity, and it's useful to invoke that at this point. Using this vector identity, we can replace the entire quantity on the left side of the equal sign with this, 1 over mu, the gradient of the divergence of A minus the Laplacian of A. So that's what we have on the left. On the right, we can just distribute j omega epsilon through the rest of the terms here, and we end up with omega squared epsilon A minus j omega epsilon times the gradient of phi plus j. Now we multiply through by minus mu. That kind of cleans up this annoying mu in the denominator over here. And we rearrange terms so that everything except for minus j mu is on the right. So when we do that, we get the Laplacian of A plus omega squared mu epsilon A minus the minus the gradient of this quantity here equals minus mu j. Now here's where the magic comes in. Since we have free choice of phi, I pointed that out before, we have complete freedom as to what we can choose for phi. The smart thing to do would be to choose phi such that the quantity in brackets here is 0. If we do that, we end up with a much simpler equation. In fact, you could probably already recognize this as a relatively simple second-order differential equation. Okay, so now let me explain these two equations. The choice that I pointed out on the previous slide, which again is not the only mathematically valid one, turns out to be a fundamental property of physics. That particular choice is known as the Lorentz gauge. And we just write it again here just for clarity. So we make this choice. It turns out from fundamental physics that this is in fact the way the universe works. We make that substitution and we get the simpler equation. The simpler equation, now that term that used to be here is gone. The simpler equation is just a second order differential equation in A, and then the right we have the sources that we're interested in. This is a inhomogeneous differential equation. In other words, it's a second order differential equation in which the we have a non-zero quantity on the right, and that non-zero quantity represents a source, specifically the volumetric current density. So now we know everything we need to know to get A from J, right? If you're given J, you can solve this differential equation. From A, then you could get H because through the defining relationship for the magnetic vector potential, and then you can get E through Maxwell's equations. But this is still more work than we would like to do. We would like to avoid having to solve a differential equation every time we want to compute the radiation from a current distribution. So now the question I'm asking here is there an easy way to use A without having to solve this differential equation every time we have a new current distribution? The answer is yes, and let me take a little diversion here to kind of set things in a form where it's a little bit easier to see that. First, let me introduce the concept of wave number. Wave number is a wave concept. It's defined as the number of radians, and that's how much phase, is incurred per unit length traversed. So you can define wave number k as 2 pi divided by lambda, because when a wave traverses one wavelength, it has incurred 2 pi radians of phase. So the wave number is 2 pi over lambda, and you can see right away it has units of either, you can write this as radians per meter, or because radians are special units and can be considered to be unitless as well, you might also write this as 1 over meters. From basic electromagnetics, we know that the wave number is related in a particular way to the constitutive parameters. And that relationship is written this way. The angular frequency, that's 2 pi f, times the square root of the permeability times the permittivity. Now in the Helmholtz equation, we had omega squared times mu epsilon here. So we can go ahead and replace that with this expression, and we get a slightly more recognizable form of the inhomogeneous Helmholtz equation that goes Laplacian of A times wave number squared times A equals minus j mu. And this is now clearly recognizable as a wave equation. So for this reason, the Helmholtz equation, as I've written it here, is also a vector wave equation. I'll point out it's not the only wave equation. It's not the only equation that's called the wave equation, but it is a wave equation in the sense that it is a second order spatial derivative plus a wave number squared. And equations of that structure are normally called wave equations. Okay, the second thing I would like to bring in here is the concept of the volumetric delta function. Now there are many delta functions, even though you might have previously had the notion that there was one delta function. In fact, there are many. Let me talk about the particular one that's of interest here, and I call it the volumetric delta function. It's defined as follows. R is just positions in space. At any position in space other than the origin, the delta function is defined to be 0. Now we don't define what the delta function is at 0. So for r equals 0 at the origin, we do not say And frankly, we're not interested in what the value is at that location. What we say instead is that if we integrate over a volume which includes the origin, then we get the quantity 1, unitless number 1. So again, the definition of the volumetric delta function is it's 0 everywhere except for the origin. And then if we integrate over a volume that includes the origin, that integration is 1. So that's the way we set it up. An important property of the volumetric delta function is that if we now have in the integrand for the volume integration some function f, which is also defined to vary as a function of position, and we also specify some position in space r naught, then we find that doing this integration gives us the function evaluated at r naught. So some people would refer to this as the sampling property of the delta function. It turns out to be a useful way to represent all kinds of fields, and in a way that's consistent with the solution of the differential equation that we are grappling with. Now, one more thing, and this really cuts to the reason why, or this really addresses the reason why I say there's different delta functions. If you decide that this is the definition of the delta function, as I have done here, then you realize that the delta function itself must have units of inverse volume. In other words, that has units of inverse meters cubed. The way you know that is because if you take inverse meters cubed, some quantity that has units of inverse meters cubed, and you integrate it over a volume, well, that contributes units of meters cubed, and that gives you a dimensionless quantity. So just dimensional analysis tells us that this must be true. And this is a useful thing to keep in mind. It reduces the chance of making a mistake when you set up current distributions later on. Okay, now the next piece that I'd like to bring in is the volumetric electric current element. So this is a current which exists at a point in space. Specifically exists at one point in space, r prime. So we know, because I've included the volumetric delta function here, that this particular current distribution is 0 everywhere except at r prime. This constant out front, J naught, that has units of amps per meter squared. And since this has units of 1 over meters cubed, then we know that we have to throw in a quantity delta V here that has units of volume. That way we get dimensional consistency. So amps per meter squared times meters cubed times 1 over meters cubed gives us amps per meter squared, which is the right unit. So this is correctly set up. By the way, you'll note that if we look at everything other than the delta function, in other words, J naught times delta V, this has units of amps times meters. I'd like to point this out because we see this show up all the time in all kinds of electromagnetic problems, amps times meters. I'll refer to it as a current moment, as many people do. Some people refer to this as current torque because you see it's amps times meters. It's analogous to mechanical torque. But current moment, amps times meters, shows up in all kinds of problems, so I just thought I'd point that out. Okay, so now we're going to solve the Helmholtz equation. The way we do this is, first of all, there are many ways to do it, but a particularly easy way to do it is to first decompose the magnetic vector potential into its Cartesian components. So what we do is we take A and we just say, look, we can write it in Cartesian form as x hat times some component A sub x, and then the component in the y hat direction times some quantity a sub y, and then the z hat component, or z hat unit vector times the some quantity which says the z component of the magnetic vector potential. Now if we take the Laplacian of the magnetic vector potential, we can distribute the Laplacian operator through those three components, as I've shown here. So the vector Helmholtz equation is now decoupled into three scalar equations. One for x, one for y, one for z. So I've written the x component equation here. And the advantage of doing this now is I've got now scalar quantities here, whereas previously I had vector quantities. So now I've got scalar differential equations to solve, a little bit easier to grapple with. And I've got 3 of them, one for x as I've shown here, and then others for y and z, which look very much the same, different subscripts. Okay, now I would like to bring in the current element concept. Here's the equation I just came up with. Here is the current element I'm interested in considering. I'm interested only in the x component. So I'll take the dot product, and I can pull that dot product inside the expression I've shown here. And so now the new form of the scalar Helmholtz equation for x looks like this. Same thing on the left-hand side. On the right-hand side, I have something that looks very similar, except now I've written explicitly the source. Okay, so now we want to solve this equation. So here is the magnetic vector potential, MVP, due to a current element. Here's the current that we have assumed. We solved the differential equation on the previous page, which is very straightforward to do. Not that's trivial, but it's a routine mathematical operation, which I think most viewers of this video are probably already familiar with. We get this. Here's the x component of the magnetic vector potential. Now you see that in this result, we have a complex exponential up here. You may recognize that as the phase factor of a wave. Specifically a phase factor of a spherical wave. And you see out front you have plus and minus signs. As you may know, waves, the sign here conveys or describes the direction of wave travel. The minus sign in that exponent indicates a wave traveling away from, here I say the antenna, but what I really mean is from the current source or the current moment. The plus sign indicates a wave which is traveling towards the current source. That's a mathematical result, and one of these results is, of course, ridiculous. You can't, sources don't generate waves which travel towards the source. They generate waves that travel away from the source. So that second possibility, the plus sign, is omitted. Now, of course, if we added some scatterers around the current sources, then the situation changes. But in free space with no scatterers, we don't expect to see waves traveling back towards the current source. So we can get rid of the plus sign, and we'll do that in subsequent slides. Now, I'd like to point out that the magnetic vector potential always points in the same direction as J naught. In general, in fact, if we have a current moment, we find out that everywhere in space, the magnetic vector potential points in the same direction as the current moment. It's one of the things that makes this particular formulation very attractive. So let me suggest some tests of understanding here. If this is new to you, or if you're rusty with it and you want to make sure you understand what's going on here, let me make 2 suggestions. One thing you could do is you could take this result, which I've just written down here without actually doing the mathematical solution from the previous slide, from the equation on the previous slide. What I would suggest you do is make sure that this is a solution to that equation. Just substitute this expression right here into the differential equation on the previous slide. Make sure it checks. That's a good idea. Also, you can check and make sure that this is dimensionally correct. In other words, does this have the right units? In other words, do I find that I have Tesla meters here or Webers per meter, given the units that I know these other quantities should have on the right-hand side? So there's 2 good ways to make sure you understand the material. Okay, now continuing, just a few more ideas about what's going on here in the solution. I've already pointed out that this is the expected phase dependence, and specifically the expected phase dependence for a spherical wave. We expect the wave phase to vary linearly with increasing distance from the source. And the source is a point in space, so that gives rise to a spherical wave. Underneath, we have simply the distance from that source. The magnitude of r minus r prime is simply the distance between the field point r and the source point r prime. So we have a 1 over r magnitude dependence. Again, we see we have a spherical wave. And then we have the source dependence. So this is our current moment here. Not much more to say about that. And then we have constants out front, mu and 4 pi. Okay, now I'd like to generalize this solution. What we've come up with so far is the x component, but we know it's a vector. It can in general have 3 components, so we can put this all back together. What we have very simply from the Cartesian decomposition I laid out in a few slides previously, I can put this all back together and I find that the total magnetic vector potential is simply given by this expression. Once again, I have the current moment, J naught times delta V, but now this is the vector. It's not a scalar quantity. And this is easy to generalize. The way I can generalize this to any current distribution, is simply to say I'm going to integrate over some volume. So instead of A, I'll say this is some differential contribution to a vector potential, and that differential contribution is due to a volumetric differential chunk of this current moment. So delta V becomes dV prime. And that's all I have to change. Now all I have to do is integrate. I integrate anywhere where J is non-zero. So here's the summary. This is really wrapping it up now. What we have found is that to get the fields from the volumetric current density, amps per meter squared, I simply integrate over that current density after multiplying it by e to the minus j k times the distance from the current source divided by the distance from the current source. It's a volumetric integral in general. And then I multiply by mu divided by 4 pi. That gives me the magnetic vector potential. Once I have A, I simply invoke the defining relationship for A to get H. So I take the curl of A to get H. And then finally I use Maxwell's equations to get E. That's just take the curl of H, divide by j omega epsilon, and that gives me E. And that's all there is to it. That's how you get the electric and magnetic fields in response to an arbitrary distribution of current in space. This concludes this lecture on radiation from electric current in free space.